Hello. So far, we've looked at the problem of linear regression and derived the optimal solution W* for linear regression. We then looked at a probabilistic viewpoint for linear regression where we assumed that y given x is W transpose x plus some zero mean noise, and we derived the maximum likelihood estimator for W. We observed that the W* coming from linear regression is exactly the same as W hat ml, the estimator coming from maximum likelihood estimation. So, this comes from maximum likelihood, and this gave us the insight that assuming the noise is Gaussian is equivalent to assuming that our error measure is squared error. So we then asked, what else do we gain by viewing this as an estimator? That is, W hat ml is an estimator for W, and what other properties of this estimator can we examine that might give us further insight into the problem itself? Now, we're going to look at one nice property of this estimator, which will give us insight into extending the linear regression problem in a particular direction. To get there, let's try to understand just how good an estimator W hat ml actually is. Recall, there's some true W, such that y given x equals W transpose x, plus some epsilon, where epsilon is Gaussian noise with mean zero and some variance, sigma squared. That was our assumption. This means that for every x in our data, y was generated using some fixed, unknown W multiplied by x plus a zero mean Gaussian noise term. This also means y given x can itself be thought of as a Gaussian distribution, with mean W transpose x and variance sigma squared. That's what we've established so far. Now, our estimator, W hat ml, is trying to estimate this true W. It's essentially our best guess for W. So, we can naturally ask how good is W hat ml as a guess for the true W? How do we even measure this goodness? Remember, W is some unknown vector living in some d-dimensional space, where d is the number of features, and W hat ml also lives in that same d-dimensional space, since it's an estimator for W. However, W hat ml comes out of an optimization problem. We maximize the likelihood, and W hat ml is the resulting solution. This optimization problem depends on our data, which includes both x and y, and we're assuming y is random, meaning y has some inherently random component. So, since y is random, the resulting best estimator for W is also going to be random, because it depends on y. If you're finding whichever W maximizes the likelihood of observing all your y's, y1 through yn, then that W becomes a function of the underlying random y's, and therefore W itself becomes a random quantity. So here's what could happen if we look at W hat ml for some particular realization of our data points, say, a specific data set, x1 through xn, paired with y1 through yn. Remember, y is random. Though we haven't assumed anything special about x, it's entirely possible that the particular y's we happened to observe aren't very representative of the true underlying W. In other words, we might have simply had an unlucky draw, where the noise added when generating our y's happened to be unusually large. If y1 equals W transpose x1 plus some noise epsilon1, and that particular noise value turned out to be quite large, then the y's we actually observe won't carry much useful information about the true W. This means that if our y's are especially noisy, the resulting W we calculate is also going to be correspondingly poor. So, we really can't judge how good W hat ml is based on just a single dataset. Instead, since y is random, and therefore W hat ml is random too, we can ask on average, how well does this random estimator W hat ml perform at estimating the true W? One way to capture this is by looking at the following quantity. We want some way to understand the overall goodness of W hat ml, how well it estimates W, on average. One natural approach is to look at the difference between W hat ml and W. Since these are both d-dimensional vectors, we can look at the squared norm of that difference, where norm here just means the ordinary Euclidean distance between the two vectors. But again, since we can't judge this based on a single sample or a single data set, we want to understand this on average, which means we need to look at the expected value of this quantity. What does that expected value actually represent? It's the average, taken over all the randomness in Y. One way to think about this concretely: imagine generating one dataset, where the Y's are randomly generated according to W transpose X, plus zero mean Gaussian noise. You compute W hat ml for that dataset, and measure how far it is from the true W. Then you repeat this same experiment many times, and average the squared distance between each resulting W hat ml and the true W across all these repeated experiments. This running average will gradually converge to the expected value of this random quantity. So, that's the essence of what we're trying to compute here, averaged over all possible data sets you might obtain. In other words, averaged over all the randomness in Y, what's the average squared deviation between W hat ml and the true W? That's the quantity we're genuinely interested in. I won't actually walk through deriving this quantity in detail, since it's not too difficult, but let's not go through the full derivation right now. Instead, I'll just tell you what this quantity works out to be. It's actually not too hard to derive, once you recall that W hat ml, as a function of x and y, is simply the pseudo-inverse of x transpose x multiplied by x transpose y, something we've already seen before. Since y is the random component here, you can use its known statistical properties to work out this expected value. But rather than deriving it here, I'll simply give you the result, and anyone interested is welcome to work through the algebra themselves. It's not too involved. So, what does this value turn out to be? It's actually a rather interesting quantity, and we'll see why shortly. The result is a sigma squared, multiplied by the trace of the inverse, or pseudo-inverse, of x transpose. This tells us something quite interesting. The average squared deviation between our estimated W hat ml and the true W is the product of two separate terms. The first term is sigma squared, the variance of the noise added on top of W transpose X. This variant should intuitively affect the quality of W hat ml, and indeed it does. If you add more noise, meaning a zero mean noise term with larger variance, you're essentially corrupting your W transpose X value with more uncertainty, and so the quality of your estimate should naturally decrease. In other words, the larger this variance, sigma squared, the larger the average deviation between W hat ml and the true W tends to be. That directly affects the quality of our estimator, which makes intuitive sense. But interestingly, this result tells us that the quality of the estimator doesn't depend only on sigma squared, it also depends on the data features themselves. Specifically, it depends on the features through the trace of the inverse of XX transpose, which is essentially the inverse of the covariance matrix of your features. So, depending on how the features themselves relate to one another, this will also affect the goodness of your estimator. It's not just the noise added on top of W transpose X that matters, it's also how the features are structured or related to each other, which is a genuinely interesting thing to notice. Now, there's some underlying data generating process here. We're given the data, and we're assuming that this data was generated by adding Gaussian noise to the true labels, giving us our observed Y's. We can't change this underlying data generating process, which means we have no control at all over sigma squared. That's simply a fixed property of the noise. But the features, x, are given to us as well. So, while we can't touch sigma squared, since that's just noise handed to us as part of the data generating process, the features themselves clearly affect the quality of W hat ml. This raises a natural question: can we somehow adjust or work with these features to obtain a better estimator, one with a smaller mean squared error. We don't yet know whether that's even possible, but if it is possible, it would have to come through this feature-dependent term. Since sigma squared is entirely off the table, that's simply noise we have to live with. Can we somehow reduce, or at least specifically focus on improving, this feature-dependent part? That's the next natural question worth exploring, and we'll look at what we can actually do about it.
Hello. So far, we've looked at the problem of linear regression and derived the optimal solution, W star for linear regression. We then looked at a probabilistic viewpoint for linear regression, where we assumed that y given x is W transpose x, plus some zero mean noise, and we derived the maximum likelihood estimator for W. We observed that the W star coming from linear regression is exactly the same as W hat ml, the estimator coming from maximum likelihood estimation. So, this comes from maximum likelihood, and this gave us the insight that assuming the noise is Gaussian is equivalent to assuming that our error measure is squared error. So we then ask what else do we gain by viewing this as an estimator? That is, W hat ml is an estimator for W, and what other properties of this estimator can we examine that might give us further insight into the problem itself? Now, we're going to look at one nice property of this estimator, which will give us insight into extending the linear regression problem in a particular direction. To get there, let's try to understand just how good an estimator W hat ml actually is. Recall, there's some true W, such that y given x equals W transpose x, plus some epsilon, where epsilon is Gaussian noise with mean zero and some variance. Sigma squared, that was our assumption. This means that for every x in our data, y was generated using some fixed, unknown W multiplied by x, plus a zero mean Gaussian noise term. This also means y given x can itself be thought of as a Gaussian distribution, with mean W transpose x and variance sigma squared. That's what we've established so far. Now, our estimator, W hat ml, is trying to estimate this true W. It's essentially our best guess for W. So, we can naturally ask how good is W hat ml as a guess for the true W? How do we even measure this goodness? Remember, W is some unknown vector, living in some d-dimensional space, where d is the number of features, and W hat ml also lives in that same d-dimensional space, since it's an estimator for W. However, W hat ml comes out of an optimization problem. We maximize the likelihood, and W hat ml is the resulting solution. This optimization problem depends on our data, which includes both x and y, and we're assuming y is random, meaning y has some inherently random component. So, since y is random, the resulting best estimator for W is also going to be random, because it depends on y. If you're finding whichever W maximizes the likelihood of observing all your y's, y1 through yn, then that W becomes a function of the underlying random y's, and therefore W itself becomes a random quantity. So here's what could happen if we look at W hat ml for some particular realization of our data points, say, a specific data set, x1 through xn, paired with y1 through yn. Remember, y is random, though we haven't assumed anything special about x. It's entirely possible that the particular y's we happened to observe aren't very representative of the true underlying W. In other words, we might have simply had an unlucky draw, where the noise added when generating our y's happened to be unusually large. If y1 equals W transpose x1 plus some noise epsilon 1, and that particular noise value turned out to be quite large, then the y's we actually observe won't carry much useful information about the true W. This means that if our y's are especially noisy, the resulting W we calculate is also going to be correspondingly poor. So we really can't judge how good W hat ml is based on just a single dataset. Instead, since y is random, and therefore W hat ml is random too, We can ask on average, how well does this random estimator, W hat ml, perform at estimating the true W? One way to capture this is by looking at the following quantity. We want some way to understand the overall goodness of W hat ml, how well it estimates W, on average. One natural approach is to look at the difference between W hat ml and W. Since these are both d-dimensional vectors, we can look at the squared norm of that difference, where norm here just means the ordinary Euclidean distance between the two vectors. But again, since we can't judge this based on a single sample or a single dataset, we want to understand this on average, which means we need to look at the expected value of this quantity. What does that expected value actually represent? It's the average, taken over all the randomness in Y. One way to think about this concretely, imagine generating one dataset where the Y's are randomly generated according to W transpose X, plus zero mean Gaussian noise. You compute W hat ml for that dataset and measure how far it is from the true W. Then you repeat this same experiment many times and average the squared distance between each resulting W hat ml and the true W across all these repeated experiments. This running average will gradually converge to the expected value of this random quantity, so that the essence of what we're trying to compute here averaged over all possible datasets you might obtain. In other words, averaged over all the randomness in Y, what's the average squared deviation between W hat ml and the true W? That's the quantity we're genuinely interested in. I won't actually walk through deriving this quantity in detail, since it's not too difficult, but let's not go through the full derivation right now. Instead, I'll just tell you what this quantity works out to be. It's actually not too hard to derive, once you recall that W hat ml, as a function of x and y, is simply the pseudo-inverse of x transpose x multiplied by x transpose y, something we've already seen before. Since y is the random component here, you can use its known statistical properties to work out this expected value. But rather than deriving it here, I'll simply give you the result, and anyone interested is welcome to work through the algebra themselves. It's not too involved. So, what does this value turn out to be? It's actually a rather interesting quantity, and we'll see why shortly. The result is a sigma squared, multiplied by the trace of the inverse, or pseudo-inverse, of XX transpose. This tells us something quite interesting. The average squared deviation between our estimated W hat ml and the true W is the product of two separate terms. The first term is sigma squared, the variance of the noise added on top of W transpose X. This variance should intuitively affect the quality of W hat ml, and indeed it does, if you add more noise, meaning a zero mean noise term with larger variance. You're essentially corrupting your W transpose X value with more uncertainty, and so the quality of your estimate should naturally decrease. In other words, the larger this variance, sigma squared, the larger the average deviation between W hat ml and the true W tends to be. That directly affects the quality of our estimator, which makes intuitive sense. But interestingly, this result tells us that the quality of the estimator doesn't depend only on sigma squared, it also depends on the data features themselves. Specifically, it depends on the features through the trace of the inverse of XX transpose, which is essentially the inverse of the covariance matrix of your features. So, depending on how the features themselves relate to one another, this will also affect the goodness of your estimator. It's not just the noise added on top of W transpose X that matters, it's also how the features are structured, or related to each other, which is a genuinely interesting thing to notice. Now, there's some underlying data generating process here. We're given the data, and we're assuming that this data was generated by adding Gaussian noise to the true labels, giving us our observed Ys. We can't change this underlying data generating process, which means we have no control at all over sigma squared. That's simply a fixed property of the noise. But the features, x, are given to us as well. So, while we can't touch sigma squared, since that's just noise handed to us as part of the data generating process, the features themselves clearly affect the quality of W hat ML. This raises a natural question: can we somehow adjust, or work with, these features to obtain a better estimator, one with a smaller mean squared error? We don't yet know whether that's even possible, but if it is possible, it would have to come through this feature-dependent term. Since sigma squared is entirely off the table, that's simply noise we have to live with. Can we somehow reduce, or at least specifically focus on improving, this feature-dependent part? That's the next natural question worth exploring, and we'll look at what we can actually do about it.
So, let me tell you what this solution means, and what the underlying methodology actually is. The methodology here is simply a Bayesian modeling approach. So, we're going to take a Bayesian approach. Just to recap, in Bayesian modeling, you have a prior over the parameter you're trying to estimate, and you have a likelihood as usual, and combining these gives you a posterior, which depends on both the prior and the likelihood. In our case, the parameter we're trying to estimate is W, which means we need a prior on W. We need some probability distribution over W, where W, remember, is a d-dimensional vector. So, across all possible d-dimensional vectors, we need some probability distribution, some density function. Since we're working in a continuous space, we'll talk about what a suitable choice for this density function might be in a moment, but first we need a prior. What about the likelihood? Well, the likelihood is something we've already established. We know that y given x is Gaussian, with mean W transpose x, and some variance, sigma squared. For ease of exposition, I'll just assume this variance equals 1. It doesn't really matter. We could equally well keep it as sigma squared and everything would proceed just as smoothly, but assuming it's 1 makes things a bit less messy to deal with. So, this is purely for simplicity. You could just as easily use sigma squared instead. Now, the question is, we've established a Gaussian likelihood, so what's a suitable prior to pair with it? By suitable, I mean we want a prior such that the resulting posterior is easy to compute. If you recall, when we had a Bernoulli likelihood in the context of unsupervised estimation, we used what's called a beta prior, which gave us a beta posterior. The major advantage there was that, since the prior and posterior shared the same functional form, in that case, the density of the beta distribution, this made updating our parameter estimates remarkably straightforward. In fact, a prior that, when combined with a given likelihood, produces a posterior of the same form, has a special name. It's called a conjugate prior. So, we'd say the beta prior is conjugate to the Bernoulli likelihood. In general, if you give me some likelihood function, and I give you back a prior such that multiplying that prior by the likelihood yields a posterior of the same form as the prior itself, then that prior is said to be conjugate to the likelihood you gave me. We've already seen that the beta prior is conjugate to the Bernoulli likelihood. So, what prior would be conjugate to our Gaussian likelihood here? Since this is a Gaussian model, well, the Gaussian density has the form e raised to some power. If you multiply e raised to some power by another expression that's also e raised to some power as your prior, the exponents simply add together, and you end up with something that's again e raised to some power as your posterior. So, intuitively, your prior should also take the form of e raised to some power, and one natural choice here is simply the Gaussian distribution itself. So, a good prior here might just be the Gaussian prior. Here's a choice for our prior. Remember, a prior encodes our belief, ahead of time, about how likely each possible value of W is. Since W is continuous, we need to encode this belief using a density function, which I'll write out now. We'll say W is distributed as a Gaussian, but remember W lives in d-dimensional space, so this is a Gaussian with mean 0, meaning a d-dimensional 0 vector, and some variance, which I'll call gamma squared, multiplied by the identity matrix. This represents a covariance matrix, since we're imposing this prior across a d-dimensional vector space. Essentially, we're saying that every individual component of W is itself a Gaussian, with 0 mean and variance gamma squared, and these components are independent of one another. So, if you wanted to actually generate a sample W from this prior distribution, you'd pick each component, W1 through WD, independently, by randomly sampling from a Gaussian with 0 mean and variance gamma squared. This is essentially our covariance matrix, a D by D matrix where the diagonal entries are all gamma squared, and everything off the diagonal is 0. That's the assumption we're making about this covariance structure. As usual, in Bayesian modeling, our goal is to compute the posterior, meaning the probability of W given our observed data, x1, y1, through xn, yn, since that's how we've assumed the data was generated, and we know this posterior is proportional to the likelihood, the probability of observing this particular data given a specific choice of W, multiplied by the prior probability of that particular W itself. That's the likelihood term, and that's the prior term, and we already know what both of these look like. The likelihood term is the product, over all n data points, since each point is generated independently, of the probability of observing y sub I, given the corresponding feature x sub I. That probability is proportional to e raised to the power of negative, the squared difference between y sub I and W transpose x sub I divided by 2, since we're assuming the noise variance is exactly 1. There's no sigma squared appearing here, just a factor of 2, and I'll leave out constant normalizing factors like 1 over the square root of 2 pi, since they're not important here, given that we're only working out to proportionality. That's the likelihood multiplied now by the prior. The prior is simply the probability of a given W, where every component is Gaussian with 0 mean and variance gamma squared. This can be written as e raised to the power of, summed over each component, from 1 to d, negative W sub I squared, divided by 2 gamma squared, since the mean is 0. Combining all these independent components together, this becomes e raised to the power of negative, the sum over all d components, of W sub I squared, divided by 2 gamma squared. We can rewrite everything together now, keeping our proportionality, as of the product, over I from 1 to n of e raised to the power of negative, the squared difference between y sub I and W transpose x sub I, divided by 2, that's our likelihood, multiplied by e raised to the power of negative 1 over 2 gamma squared, times the sum over all d components of W sub I squared, which is simply the squared norm of W. So, this whole prior term becomes e raised to the power of negative, the squared norm of W, divided by 2 gamma squared. So, this is the form our posterior takes. Of course, there will be normalizing constants to ensure this is a proper density function, but the posterior is proportional to this combined expression. This means, if we want to find the maximum a posteriori estimate, how would that actually look? Let's work this out, maximizing the posterior, since normalizing constants don't affect where the maximum occurs with respect to W, is equivalent to maximizing the logarithm of this expression instead. So, W hat MRP, our maximum a posteriori estimate, equals whichever W maximizes the log of this combined likelihood times prior expression. Taking the log converts our products into sums, giving us the sum, over I from 1 to n, of negative, the squared difference between y sub I and W transpose x sub I, divided by 2, plus negative, the squared norm of W divided by 2 gamma squared. This is equivalent to minimizing the negative of this expression instead. So W hat mp becomes whichever W minimizes 1/2 times the sum over I from 1 to n of the square difference between y sub I and W transpose x sub I plus 1 over 2 gamma squared times the squared norm of W, since flipping from maximization to minimization flips the sign, and the negatives cancel out nicely. So, now we can ask, what does the solution to this look like? Previously, with maximum likelihood, we only had this first term. Now we've added an extra term, 1 over 2 gamma squared, multiplied by the squared norm of W. Let's see what solving this combined expression actually gives us. As before, we can take the gradient, set it equal to 0, and solve for W hat mp. I'd strongly encourage you to work through this yourself. I'll tell you what the gradient turns out to be, but please do try it on your own first. If we think of this whole expression as some function, f of w, then the gradient of f with respect to w works out to x transpose times w minus x transpose y, plus w divided by gamma squared. Please verify this yourself, it's a fairly direct step, and you should be able to work through it, given everything we've covered so far. Setting this gradient equal to 0, we get to W hat mp equals the inverse of the quantity x transpose plus 1 over gamma squared times the identity matrix, all multiplied by x transpose y. This is our maximum a posteriori solution. This should look quite familiar. This solution is exactly the same estimator we pulled out of thin air earlier, where we argued that, for some particular choice of lambda, in place of 1 over gamma squared here, the estimator would achieve lower mean squared error. Here, we're arriving at the exact same estimator, but through a completely different route, starting from a Bayesian model, where we impose a prior directly on W, and then ask what comes out as the maximum a posteriori estimate under that prior. It turns out that what comes out is exactly the same estimator, just expressed using a different constant. Previously, we were cross-validating to find a good value for lambda. Here, you'd do exactly the same thing, cross-validating to find a good value for gamma squared instead. It's fundamentally the same idea, since, at the end of the day, it's just a single number you're trying to tune to see which value best fits your data, and this can absolutely be cross-validated in practice. So, what's the takeaway from this whole exercise? We've arrived at something genuinely interesting. Maximum a posteriori estimation for linear regression, using a Gaussian prior, specifically a zero-mean Gaussian with covariance gamma squared times the identity, where that 0 is a d-dimensional zero vector, since we need a prior spanning the entire d-dimensional space for W, turns out to be exactly equivalent to the new estimator we introduced earlier. This gives us a much more principled way of understanding where that estimator actually comes from. We started with an ordinary linear regression problem, solved it directly, and got a solution. Then we reframed the same problem as an estimation problem, arriving at a maximum likelihood estimator. Then we looked at a Bayesian version of this same setup, and found that this Bayesian approach gives us a new estimator, one that, in practice, often performs better.
Let's take a step back and look at everything together. From a high level, everything we've covered so far about linear regression can be summarized as follows. Linear regression gives us W hat ml, defined as the value of W that minimizes the sum, over I from 1 to n, of the squared difference between W transpose x sub I and y sub I. Now, what we introduced is a new estimator, a MAP estimator usually called W hat R, where R stands for ridge and name with roots in classical statistics, though we won't get into that etymology here. This estimator is, for our purposes, the value of W that minimizes the sum, over I from 1 to n, of the squared difference between W transpose X sub I and Y sub I, but with an added second term, some scaled version of the squared norm of W, specifically, plus some lambda multiplied by the squared norm of W. This problem is called the ridge regression problem, where you add this extra term onto your original error, or loss. That original term was our usual loss, and now we're adding this extra term, which, as we saw, has a natural Bayesian interpretation, or, alternatively, you can simply think of it as something added specifically to help reduce mean squared error. This added term is typically called a regularizer. So, essentially, what we're saying is that, in addition to the loss itself, we want to add some additional quantity that penalizes certain types of W, effectively expressing a preference for some W's over others. When I say we're placing a prior on W and doing Bayesian modelling, that's exactly what we mean. We're expressing a preference for certain kinds of W. And recall, the prior we used was a Gaussian, with mean 0, that 0 being a vector, and some variance. That variance term is exactly what becomes this lambda. So, lambda is what's called a hyperparameter, something we cross-validate for, and it corresponds directly to this variance term from our prior. But what does the prior itself actually tell us? If the prior has mean 0, it means we're implicitly preferring W's whose overall length is as small as possible. In fact, taken to the extreme, we'd prefer W to be entirely 0, which sounds strange at first. Why would we want that? Because our prior, being a Gaussian centered at 0, has its highest probability, its mode, sitting exactly at 0. One way to think about this is that this second term, coming from the prior, lambda times the squared norm of W, is essentially trying to pull our answer toward 0, trying to make the individual components of W as small as possible. This happens because we're penalizing the squared norm of W, which is simply a measure of W's overall length, so we want that length to be small. We're pulling W toward 0, while the first term is simultaneously trying to make the loss itself as small as possible. If it happens that multiple different W's achieve the same loss value, then, among those, we'd prefer whichever W has the smallest overall length, meaning the one with the most small-valued components. Of course, you generally can't push W all the way to 0, since a completely 0 W would be entirely useless for prediction. But what's the actual motivation behind pulling W toward 0 in the first place? The idea is this: if you're working with a large number of features, say 10,000, or even 1,000,000, many of these features could potentially be redundant. For example, maybe you have height as a feature, weight as a feature, and then, say, some sensor that happens to capture something like twice the height plus 3 times the weight, just as a simple illustrative example. When you have many features like this, redundancy can easily creep in. This matters because, if your label Y is meant to be represented by some linear combination of these features, and some features are redundant, then multiple different linear combinations of weights might end up explaining that same label equally well. So, what we're really saying is, among all these equally valid combinations, prefer the one where the overall set of weights has the smallest possible length. In other words, avoid unnecessarily relying on multiple redundant features at once. Let's walk through an example. Suppose you have height as one feature, weight as another, and then twice the height plus 3 times the weight as a third feature. And suppose your label is a noisy version of 3 times height plus 4 times weight. There are multiple ways to arrive at this same target value. One approach is, suppose you assign a weight of 1 to each of the 3 features, height, weight, and this third combined feature. Adding these 3 contributions together, weighted equally at 1 each, gives you exactly 3 times height plus 4 times weight, matching your label perfectly. But you could just as easily explain that same label a different way. Suppose you instead assign a weight of 0 to height directly, and use some other combination of coefficients on the weight feature and this third, combined feature, such that some constant times weight, plus another constant times the combined feature, twice height plus 3 times weight, also produces exactly the same target value. So here, you're already starting to avoid relying on redundant features simultaneously. Another possible combination might simply use weights of 2, 3, and 0 across these 3 features, and still land on the same result. So, in some sense, you might be genuinely better off deliberately avoiding these redundant features wherever possible. In other words, pushing as many feature weights towards 0 as you reasonably can, on the assumption that most redundant features probably don't need substantial individual weight. But, of course, whatever features are genuinely necessary to minimize the loss, those you'll naturally want to retain. That's essentially what this prior is quietly trying to encourage. Now, what exactly is lambda doing here? Recall, lambda corresponds to 1 over gamma squared, where gamma squared was our prior's variance. If you hold a very strong belief that most features are redundant, meaning you expect many components of W to sit very close to 0, that correspond to a small variance in your prior, a small gamma squared, meaning most of the probability mass concentrates tightly around 0, and if gamma squared is small, then 1 over gamma squared, or lambda, becomes correspondingly large. This means the minimization problem imposes a large penalty for allowing W to grow. So, if you were to choose a W with larger overall weights, meaning a large squared norm, you'd incur a correspondingly large penalty, proportional to lambda, which itself grows large precisely when your prior variance is small. In other words, if you genuinely believe most of your features are redundant, then choosing a W with many large-valued components becomes strongly discouraged. So, your resulting W naturally won't end up looking like that, even after minimizing this combined objective. You can think of these two terms as balancing two competing goals of how much loss you're willing to accept versus how much feature redundancy you're willing to tolerate. That's essentially what ridge regression is trying to accomplish. Now, you might reasonably ask why not try to directly push as many components of W to exactly 0 as possible. Is ridge regression really the only way to approach this? Are there other ways to think about this kind of regularization? Or, put differently, is there a better, perhaps more geometric way to understand ridge regression, one that might lead to better algorithms, or slightly different formulations of the linear regression problem altogether? The answer to all of these questions is yes. And this will lead us towards something different, a modified version of linear regression. To get there, we need to understand ridge regression through a slightly different geometric lens, and that's exactly what we'll start exploring next. Thank you.
So far, we've been looking at supervised learning, specifically the problem of linear regression, and we wrote down 2 different formulations for it. One was the basic formulation, which we call standard linear regression, where we minimize a loss function of the form, summed over each data point, the squared difference between W transpose X sub I and Y sub I. We also wrote down what's called the ridge regression problem, which differs slightly from standard linear regression in that it doesn't just minimize the loss, it also minimizes an additional penalty term of the form lambda times the squared norm of W, where, in this case, the norm is simply the L2 norm, meaning the sum, over I from 1 to d, of W sub I squared. This is exactly the squared length of the vector W. If you think of W as a vector pointing somewhere in space, this is the squared length of that vector. We called this the regularization part of the objective. We argued that we want to use this regularizer because we want to push the values of W toward 0, with the hope that, if there are redundant features, you won't end up giving weight to both of them, only one feature effectively gets picked. That was the high-level reasoning behind this regularizer. But the question we want to ask and answer today is there a way to understand more precisely what's happening here with regularization? In particular, Can we relate the linear regression solution and the ridge regression solution to each other, and will that give us insight into what this regularizer is actually doing? And if we understand this better, can we perhaps find a different way to approach the regression problem altogether? These are the high-level questions we're going to explore today. So, our goal is to first understand how the solutions to linear regression and ridge regression relate to each other, and see if something useful emerges from that. To understand this, we'll work with a simplified setup, looking only at two-dimensional data, meaning just two features, say height and weight. This means our W will also be a two-dimensional vector, letting us visualize what's called the parameter space. Remember, the parameter we're searching for, if you think of this as an estimation problem, is simply the vector W, which, in this case, is a two-dimensional vector. Picture a two-dimensional plane, with one axis representing the first component of W, and the other representing the second component. Our W can take any value across this entire plane, including negative values. It's the entire two-dimensional space, where our parameter is free to live. Now, suppose we have a dataset, and we solve the standard linear regression problem without any regularizer, which, as we've already seen, is equivalent to solving the maximum likelihood problem, assuming Gaussian noise. Suppose we solve that and get our solution, W hat ml, sitting somewhere in this two-dimensional space. The question we are asking now is, where does W hat R, the solution to the ridge regression problem, end up? Suppose I tell you W hat ml sits at some particular point in this two-dimensional space. Can we reason about where W hat R, the ridge regression solution, ends up relative to it? To understand this, we need to understand what ridge regression is actually doing. Let me write down the ridge regression problem again and find the W that minimizes the loss, the sum over data points of the squared difference between W transpose X sub I and Y sub I, plus lambda times the squared norm of W. Now, while this is how we typically write down and solve this problem, one can argue, without proving the equivalence here, that this is actually equivalent to a constrained optimization problem. Remember, in the original formulation, W is entirely unconstrained, but this turns out to be equivalent to a different problem minimize over W in d-dimensional space. The exact same loss function, the squared difference between W transpose X sub I and Y sub I, but this time without any added regularizer term, subject instead to the constraint that the squared norm of W is less than or equal to some value, theta. Here's what that means. If you give me some lambda, and I solve the original ridge regression problem using that lambda as the regularization hyperparameter, there exists some corresponding theta, depending on that lambda, such that if I instead solve this constrained problem, minimizing the loss subject to the squared norm of W being at most theta, I get exactly the same W as I would have gotten from the original, unconstrained ridge regression problem. This equivalence is a known result. What does this tell us? To be precise, for every choice of lambda greater than 0, there exists some theta such that the optimal solutions of these two problems, let's call them problem A and problem B, coincide exactly. So, what does this actually give us? It tells us that we can either think about ridge regression through problem A, or equivalently, through problem B. Remember, our original goal was to understand the relationship between the maximum likelihood solution from standard linear regression and the ridge regression solution. Does this alternative formulation actually help us understand that relationship better? Let's see what it means. This tells us that there's an implicit constraint dictating where we're allowed to search for our W. The moment I give you a particular lambda, this is equivalent to saying find a W such that the squared norm of W is less than or equal to some theta. In our two-dimensional picture, what does this actually mean? Saying a squared norm of W is at most theta means, in 2 dimensions, that W1 squared plus W2 squared is less than or equal to theta, when equality holds. This is exactly the equation of a circle. So, the condition less than or equal to theta means we're restricted to every point within some circle centered at the origin, with radius equal to the square root of theta. This is the entire region of possible W's that ridge regression is allowed to search within. We're trying to minimize the loss, but now W isn't free to range over the whole plane. It's constrained to lie within this circle. So, this circle represents exactly the set of all W such that the squared norm of W is at most theta. Now, our earlier solution, W hat ml, might well sit outside the circle, since there was no constraint at all on the length of W when we solved the original, unconstrained linear regression problem. But because of this regularizer, we're now implicitly restricting ourselves to searching only within this circle, so where exactly within this circle does W hat R end up? To figure that out, we need to look a bit more closely at W hat ml itself. Let's first ask what is the loss, or objective function value, of linear regression, evaluated specifically at W hat ml. You minimize the loss function, you get W hat ml, and you can ask what loss that particular solution actually incurs. It need not be zero. Since your data points might not follow an exactly linear relationship, there could be noise, meaning even the very best possible W will still incur some non-zero loss. That loss is simply the sum, over I from 1 to n, of the squared difference between W hat ml transpose x sub I and y sub I, since W hat ml transpose x sub I is exactly what W hat ml predicts for each data point, and y sub I is the actual observed value, so the squared difference between them is the loss. Let's call this overall objective function f. So, f evaluated at W hat ml gives us this minimal loss value. Think of f as a function that takes some W and tells you the corresponding loss. What do we know about f evaluated at W hat ml? By construction, by definition, since W hat ml was specifically chosen to minimize this loss, f at W hat ml is the smallest possible value this function can take. No other W can give a strictly smaller value. So, here's an interesting question. Let's consider the set of all W's whose loss, meaning the objective function evaluated at that W, equals the minimum loss achieved at W hat ml, plus some fixed positive constant, c. In other words, we're looking at W's whose loss is exactly c more than the minimum possible loss, where c is some positive number. Such W's will certainly exist. Among all possible W's with higher loss, we specifically care about those whose loss exceeds the minimum by exactly this amount c. For example, if the loss at W hat ml is 100, we're asking which W's have a loss of exactly 100 plus c. Let's define this set to call it S sub c, the set of all W such that f of W equals f of W hat ml plus c. What does every W belonging to this set satisfy? This is an important, though fairly simple, observation. Every W in S sub c satisfies the following, writing the loss in vector notation, the squared norm of x transpose W minus y, using x as the matrix, whose columns are data points, so x transpose W gives us exactly those W transpose x sub I values we've seen before, and the squared difference from y is exactly our objective function, f of W. Since W belongs to S sub c, this must equal the squared norm of x transpose W hat ml minus y, which is f of W hat nl, plus this extra c. Now, one can carry out some algebraic simplification here. I'll spare you the detailed algebra, but I'd encourage you to work through it yourself. It involves expanding both sides, writing each squared term as a product of the corresponding vector with its own transpose, which gives 4 terms on each side, several of which cancel out. After simplifying, you arrive at the following equation: the quantity W minus W hat ml transposed multiplied by XX transpose multiplied again by the quantity W minus W hat ml equals some constant, let's call it C prime, not the same as our original C, just some resulting constant. If you actually carry out the simplification, you'll get the exact value of this constant, but the specific value doesn't matter much for our purposes, so I'll just call it a constant. What does this constant depend on? It depends on C, obviously, on our data, and on W hat ml itself, but crucially, not on W. We're going to treat this whole equation as a function of W, and see what that tells us. So, we can write this as a given W hat ml, given our data, and given some choice of C, we can ask, where is the set of all W's that produce exactly C more error than W hat ml? Such W's satisfy exactly this equation, the quantity W minus W hat ml transposed times XX transpose times the quantity W minus W hat ml equals some constant. Let's pause and understand what kind of equation this actually is. Suppose, just for a moment, that XX transpose happened to equal the identity matrix. It generally won't, but let's use this to build intuition. If XX transpose were the identity, this equation would simplify to the quantity W minus W hat ml transposed times the identity times the same quantity equals some constant, which is just the squared norm of W minus W hat ml equal to some constant. Where would such W's lie? They'd lie exactly on the circumference of a circle centered at W hat ml. So, if W hat ml sits at some particular point, these W's would form a circle around it. But this is only true if XX transpose happens to be the identity matrix. In general, XX transpose is some other matrix, which means this set is no longer exactly a circle. Instead, since we're effectively linearly transforming the vector W minus W hat ml through this matrix before taking its squared length, this circle gets stretched into an ellipse. So, what's the actual usefulness of all this? Here's the insight we've gained if you give me some constant, say 10, and ask where the set of all W's lie that produce exactly 10 units more loss than W hat ml. The answer is that they lie on an elliptical contour surrounding W hat ml. Let's translate this back into our picture. Going back to our parameter space, we had W hat ml sitting somewhere, and we also had this circular region representing where ridge regression is constrained to search for W hat r. That part remains unchanged, nothing new there yet. But now, incorporating this new insight about elevated loss levels, where do the W's lie that incur slightly more loss than W hat ml, our analysis tells us these satisfy this elliptical equation. The quantity W minus W hat ml transposed times XX transpose times that same quantity equals some constant, forming an ellipse centered at W hat ml. These are all representative sketches. The actual shape depends on your specific data. I'm just giving you a general sense of what this looks like. Picture this elliptical contour representing a loss exactly 10 units above the minimum. If we increase that threshold to 20 units above the minimum, we get a slightly larger, concentric ellipse, still centered at W hat ml. Increasing it further gives an even larger ellipse, and further still, an even larger one. At some point, one of these expanding elliptical contours will just touch, or intersect, our circle, the region defined by the constraint on W's squared norm. Recall that circle represents exactly the constraint bounding where ridge regression is allowed to search, the set of all W such that the squared norm of W is at most theta. Since W hat ml sits outside this circle, ridge regression is necessarily going to incur more loss than W hat ml. There's no way around that, since W hat ml was already the absolute minimum. But we're exactly within the circle, does the ridge solution end up? It's exactly at the point where these expanding elliptical contours, centered on W hat ml, first touch the circle. At that point, you're incurring the smallest possible additional loss relative to W hat ml, while still satisfying the constraint. Moving in that particular direction increases your loss, so you want to move just far enough, in exactly the right direction, to reach the boundary of the circle as early as possible, without growing your loss any more than absolutely necessary. That point, where you first touch the circle's boundary while incurring the least additional loss, is exactly your ridge regression solution, W hat R, since this is precisely equivalent to solving the original problem, finding the W that minimizes loss, subject to the constraint that W lies within, or on the boundary of, this circle. So, what conclusions and insights can we draw from all of this? This leads us to something quite interesting. First, a ridge regression pushes feature values towards 0. Why? Because we're searching for W within a circle whose radius is smaller than the length of W hat ml, meaning W hat R ends up being a shorter vector than W hat ml. So, ridge regression effectively reduces the overall length of W, indirectly pushing its components closer to 0. But here's what doesn't happen. These feature values don't necessarily become exactly 0. Looking at our resulting W hat R, none of its individual components are actually exactly 0. They are simply smaller in magnitude. This is a simplified illustrative example, but it captures the main idea well. The overall length shrinks, but the point where the elliptical contour first touches the circle doesn't necessarily land on an axis where some component would be exactly 0. Why does this distinction actually matter? Because if a particular feature's weight becomes exactly 0, we know definitively that feature is entirely useless, and we can discard it completely. But if it merely becomes small, rather than exactly 0, we're left in a somewhat ambiguous position. Should we discard it, or keep it? It becomes genuinely unclear. So, now that we have this geometric insight into how regularization actually works, the natural question becomes, can we use this insight to design a different way of regularizing linear regression, one that actually encourages some components of W to become exactly 0, rather than merely small? In other words, can we modify this region we're searching within, since that's really what the regularizer is fundamentally doing, imposing a constraint on where we search for W, so that these elliptical contours are more likely to first touch the boundary at a point where some feature values are exactly 0, rather than just small. That's the motivation for what comes next.
Now that we have this geometric insight into how regularization works, can we use it to come up with a different way to regularize our linear regression, one that actually encourages our W's to take exactly 0 values? In other words, can we change the region we're searching within for W, which is really what a regularizer does, imposing a constraint on where we search, so that these elliptical contours are more likely to touch that region at a point where some feature values become exactly 0, rather than merely small? So, this is our motivation for trying to get what's called a sparse solution, meaning a solution with many exact zeros, an alternative way to regularize, and we'll see why this turns out to be a better approach is to use the L1 norm instead of the L2, or squared L2 norm. What does that mean? What is an L1 norm? The L1 norm of a vector W is defined as the sum, over I from 1 to d, of the absolute value of each component. We're simply summing up absolute values. What does this mean in practice? If we regularize using the L1 norm, our objective becomes minimizing, over W, the same loss as before, the sum over data points of the squared difference between W transpose X sub I and Y sub I, plus lambda times the L1 norm of W, that sum of absolute values. Now, by the same kind of equivalence we discussed earlier, this is equivalent to minimizing, over W in d-dimensional space, the same loss function, But now, for a given choice of lambda, subject to some corresponding theta, constraining the L1 norm of W, this theta won't necessarily be the same value as the theta we used for the L2 case, but we'll just reuse the same symbol, theta, for convenience, since the specific value doesn't matter for our discussion. The key point is that you can express this same L1 regularized problem as a constraint optimization problem, where the constraint now applies to the L1 norm of W rather than its squared L2 norm. So, what does it actually mean to have an L1 constraint on W? How does our picture change? First, let's ask, where do the W's satisfying an L1 constraint actually live? Let's go back to our picture. Previously, we had our L2 constraint region, the set of all W's such that the squared norm of W is at most theta, forming a circle. Now, we're no longer searching within that circle, we're instead searching within the region where the L1 norm of W is at most some other theta. Where does that region actually look like? If you think carefully about it, this region turns out to be a diamond shape, centered at the origin, with its corners touching the axis. This is the region defined by the L1 norm being at most theta. This is now the region we're searching within for our W. Why is this actually helpful? Again, this is an intuitive argument. Suppose we again have W hat ML sitting somewhere, with our elliptical loss contours surrounding it. As before, the loss increases outward in these elliptical rings. The hope here is that, as these ellipses expand, they are more likely to first touch this diamond-shaped region at one of its corners, rather than along the flat edge. It's not absolutely guaranteed that this will happen, but if it does, and if we compare this to what would happen with a circular L2 constraint, since the L2 region bulges outward smoothly, the ellipse tends to touch it sooner, along a curved boundary, at a point away from the axis. With the L1 constraint, though, since the diamond has these sharp corners, you might have to expand a bit further before the ellipse touches the boundary, and it's more likely to make first contact right at one of those corners. Let's call the resulting solution W hat L, standing for the L1 regularized solution. What's the significance of landing exactly on one of these corners? At any such corner, only one of the two features has a non-zero value. The other feature's weight is exactly 0. Since we only have two features in this simplified example, a genuinely sparse solution would mean picking just one feature. You either use both features, or you're forced to pick just one. You can't meaningfully set both weights to 0. That would be a useless solution entirely. Here, sparsity specifically means selecting only one feature, and the only points in this diamond region where that happens are exactly these 4 corner points, where one coordinate is precisely 0. Now, in this simplified two-dimensional case, one could certainly argue that, depending on exactly where W hat ML sits, and how these elliptical contours happen to be oriented, you might not always land exactly on one of these corners. That's a fair point. But in higher dimensions, what's typically observed in practice is that using an L1 regularizer makes you considerably more likely to land on a genuinely sparse solution compared to an L2 regularizer. So, the intuitive argument here is that the L2 constraint region has the smooth, rounded bulge, whereas the L1 region is flat along its edges, with sharp corners, meaning you tend to move past the smooth bulge and instead land right on one of these sharp corner points, where many components end up being exactly 0. This is just an intuitive argument. Of course, one can actually prove certain formal guarantees about when L1 regularization is guaranteed to produce sparse solutions. That's something explored in more advanced courses, and we won't go into that level of detail here. For now, it's enough to understand that using an L1 penalty instead of an L2 penalty tends to produce noticeably more sparse solutions. This particular approach to linear regression, using L1 regularization, has a specific name. It's called lasso. LASU is an acronym standing for least absolute shrinkage and selection operator. What does that name actually mean? Each word here corresponds to something we've already discussed. It's called least because we're minimizing some loss. It's called absolute because we use the L1 penalty, involving a sum of absolute values. It's called shrinkage because the overall length of W gets shrunk. We're restricting our search to a region where W has a smaller overall length, making this a shrinkage operator. In fact, the L2 approach is also, technically, a kind of shrinkage operator, since anything that minimizes the length of the parameter space you're searching within counts as a shrinkage technique, just applied differently here, using absolute values rather than squared values. And it's called selection, because the underlying hope isn't just to shrink W's length, it's to actually select the genuinely important features. You want to push as many components of W to exactly 0 as possible, so that whichever components remain non-zero correspond to the features that are actually important for minimizing the loss. This lets you effectively select just those important features and discard the rest, making this a genuine feature selection technique too. An operator is simply a fancier way of saying it's a regularizer. So, this is what's called the LASU penalty, or the LASU problem. It's also very widely used to solve linear regression problems, especially when you're dealing with a large number of features, and you suspect that many of them are likely redundant or useless. In such cases, LASU tends to push those redundant feature weights to exactly 0.
So now the question is, why don't we just always use LASU? If it gives us the benefit of pushing values to exactly 0, why would anyone still want to use ridge regression when LASU seems easier? Are there still some advantages to using ridge over LASU? Let me point out a few things. The first point is that LASU does not have a closed-form solution. Remember, our ridge regression problem had a closed-form solution. The inverse of x transpose plus lambda times the identity multiplied by x transpose y. LASU, on the other hand, doesn't give us that luxury. We can't simply take the derivative, set it to 0, and solve directly, because the LASU objective itself isn't exactly differentiable everywhere. Specifically, the penalty term isn't differentiable at 0, so we can't take a gradient and set it to 0 to solve for the optimal solution directly. So, how do we actually solve this problem? We use what are called subgradient methods. Recall, ordinary gradient descent methods work by following the negative gradient direction. But for problems where differentiability becomes an issue, meaning the gradient doesn't exist everywhere, you can still solve the problem iteratively, using something called a subgradient instead of a gradient. A subgradient behaves just like a gradient wherever a gradient actually exists, but at points where it doesn't, a subgradient instead represents a direction along which the function is still completely lower bounded. Let me give you some intuition for what subgradients look like, without going into excessive detail. Suppose you have some piecewise linear function made up of different linear pieces meeting at certain points. At one of these meeting points, say, where two different linear pieces intersect, the function isn't differentiable. There's no single well-defined gradient there, but a subgradient, in this context, is essentially a line that completely lower bounds the function at that point. In fact, at such a meeting point, there can be multiple valid subgradients, multiple different lines that all lower bound the function there. At any other, smoother point, where the function actually is differentiable, there's only one such line, its ordinary gradient, and no other line can completely lower bound the function at that particular point. So, these lower bounding lines are called subgradients, and where the function happens to be differentiable, that unique subgradient is simply the ordinary gradient. Why is this relevant for us? Because the L1 penalty behaves exactly like this. The absolute value function looks like two linear pieces joined together at 0, forming a sharp corner, not differentiable exactly at that point, but it does have subgradients there. At that corner, many different lines can lower bound the function, each with its own slope, and each qualifies as a valid subgradient. In fact, for the one-dimensional absolute value function, the subgradient at 0 can be any slope between -1 and +1. Any line with a slope in that range will completely lower bound the absolute value function at that point, and each qualifies as a subgradient. Let me give you the formal definition of a subgradient, and then we'll wrap up this discussion. A subgradient, some vector, in d-dimensional space, of a function f mapping from d-dimensional space to the real numbers, at a particular point x, is defined as follows: for every possible value z, the function's value at z must be greater than or equal to f evaluated at x, plus the subgradient vector, transposed, multiplied by the quantity z minus x. In other words, if you linearize the function at x, using this subgradient vector g, the actual function must lie entirely above that linearization everywhere. Going back to our earlier example, the piecewise linear function with a corner pick any point z, the function itself takes some value there, f of z. If the subgradient slope is g, then the linearized value at that point would be f of x plus g times the quantity z minus x. And you can see that f of z always sits above this linear approximation, no matter which z you pick. The actual function stays above this line. If you can find some g that satisfies this condition for every possible z, that g qualifies as a subgradient. So, what's the actual use of subgradients? Here's why they're useful. If the function you're trying to minimize is convex, then subgradient descent is an algorithm you can use in place of ordinary gradient descent, and this algorithm is still guaranteed to converge. What this means is that, even if your function isn't differentiable everywhere, as long as it's nicely behaved, specifically convex, you can still converge to the function's minimum by moving along the negative of a subgradient instead of the negative of an ordinary gradient. Even though there might be multiple valid subgradients at a non-differentiable point, it doesn't matter which one you pick. You can choose any arbitrary subgradient at that point and move in the negative direction along it, and as long as the overall function is convex, subgradient descent is still guaranteed to converge to the optimal solution. Why does this matter for us? Because the lasso problem happens to be a convex problem, the loss function itself is quadratic, and the L1 norm is a convex function, and the sum of convex functions remains convex, so the overall lasso objective is a convex optimization problem. And since we're minimizing a convex function, we can use something like subgradient descent to solve it. That said, this isn't the only way to solve the lasso problem. There are other specialized methods available too. We won't cover those methods in detail here, but I'll just mention that they exist, special purpose methods, since this is a particular kind of problem, a quadratic loss combined with an L1 penalty, and you can design specialized algorithms tailored specifically to that structure. For lasso specifically, one example is a method called IRLS, the iterative reweighted least squares method. Again, we won't go into detail on this method in this course, but the essential idea is that, since we already know how to solve ordinary least squares easily, in closed form, that's just standard linear regression, you can use that as a kind of building block or black box to help solve the lasso problem instead. Essentially, this approach takes advantage of the specific structure in the lasso problem that it's fundamentally a linear regression problem combined with an extra penalty, and uses its structure to design a specialized method like IRLS. Alternatively, you can simply use a general-purpose gradient descent style algorithm by recognizing that our overall objective, the loss plus the L1 penalty, is convex even though it isn't differentiable everywhere, and using subgradient descent methods instead. All of these approaches work. We just need to keep in mind that there's no closed form solution to the Lasso problem, and that's really the main takeaway from this part of our discussion. There's no closed form solution for Lasso, so we can't simply plug in our data and labels and get a direct, closed form expression for W. We have to do some extra computational work. It's important to keep this in mind. While Lasso does give you a sparse solution and other nice properties, it's not quite as straightforward to solve as ridge regression, which gives you a clean, closed-form solution directly. You can also use stochastic gradient descent for ridge regression if you'd like, particularly useful when your data size, n, or feature dimension, d, is very large, but for smaller values of n and d, you can simply use the closed-form solution directly. Lasso, on the other hand, never offers a closed-form solution, so you always have to rely on either general optimization techniques, like subgradient descent, or specialized methods, like IRLS. So, with this, we conclude our discussion of the regression problem. I want to summarize, at a high level, everything we've covered so far in regression, before moving on to the next part of the course. In regression, we first noted that you can solve a least squares objective, minimizing squared error, and that this has a clean closed-form solution. We looked at its geometric interpretation and had a broader computational discussion, ultimately arriving at the stochastic gradient descent algorithm as well. We then noted that if you introduce a probabilistic perspective, linear regression with squared loss turns out to be exactly equivalent to maximum likelihood estimation, and since it's a maximum likelihood estimator, we naturally asked whether there's a Bayesian counterpart to this, which led us to the regularized version of linear regression, the ridge regression problem, where we used an L2 regularizer, equivalent to imposing a Gaussian prior with mean 0 on W itself. We then observed that, while the L2 regularizer is effective at pushing W's components close to 0, it doesn't necessarily push them to be exactly 0. To achieve exact zeros, we examined the geometry of the problem more carefully, and found that an L1 regularizer works better for this purpose, leading us to the Lasso problem, the least absolute shrinkage and selection operator, which combines squared loss with an L1 regularizer. We also briefly discussed how to actually solve the Lasso problem, involving subgradients and other specialized techniques like IRLS. That's the overall summary of linear regression. I also want to point out that, in practice, people use all sorts of regularizers. There are hybrid approaches too, combining Lasso and ridge regularization together, known as the elastic net penalty, and so on. There's really an entire, rich landscape of regularizers out there if you believe your W should satisfy some particular structural constraint. For example, maybe your features naturally fall into groups, where you know certain groups of features should either be selected together or excluded together. These are domain-specific constraints that can arise, and you can translate them into custom regularizers and then solve the resulting regularized problem accordingly. All of this has been studied extensively. What we've covered in this course are some of the most basic, widely used types of regularizers, but as machine learning practitioners, you should also keep in mind that if you have specific domain knowledge about the structure you expect your solution to have, in some future problem you're working on, you can often translate that knowledge into a more meaningful, tailored regularizer, rather than simply defaulting to ridge or Lasso penalties. With this, we'll complete our discussion of regression in this course and move on to the next part of the course, where we'll discuss supervised learning from a classification perspective instead. Thank you.
Greetings for the day. Today we'll be going through the companion material generated for week 6 of the Machine Learning Techniques course, which covers ridge regression. lasso regression, and various cross-validation methods. To illustrate the effectiveness of rouge and lasso regression, we'll generate a dataset with some correlated features. In this particular example, I'm generating a 100-sample dataset, each with 50 features. The first 25 features aren't correlated with each other at all. They're completely uncorrelated, while the other 25 features have some linear correlation added between them. I won't walk through this code in great detail, though I'd encourage you to look through it yourself. But if you look at the correlation matrix for this dataset, you'll see the first 25 features aren't very correlated, shown here in green, indicating close to zero correlation, whereas the yellow and purple regions indicate strong positive or negative correlation. To generate our labels, since we have our dataset, we also need a weight vector, W, and some noise. So, we'll create W as a sparse vector, with only 10 out of the 50 features being non-zero, and our error vector will have variance 0.1. This corresponds to the standard deviation on this particular scale. Using these, we generate our labels, Y. Our goal now is to figure out what this underlying W actually is. Recall, what was covered in week 5 was maximum likelihood estimation, and its closed form solution is the pseudo-inverse of XX transpose multiplied by X transpose Y. This corresponds to the maximum likelihood estimate, also called the ordinary least squares estimate. Now, we want to improve on this, so let's investigate how good this estimator actually is. We'll use a metric for that, called mean squared error. If we call our estimate W hat, mean squared error essentially measures the squared Euclidean distance between the true value of W that we originally generated and the estimator we're currently evaluating. This formula can also be decomposed into another form, expressed in terms of the bias and variance of the estimator. That decomposition is the mean squared error equals the trace of the covariance matrix of our estimator, plus the squared norm of the estimator's bias. The derivation for this is included in the notebook. Given this, we can apply this bias variance decomposition to our ordinary least squares estimator, and we find that, for this estimator, the bias is exactly 0, it's an unbiased estimator, so only the trace term matters, and that trace, the trace of the covariance matrix of W hat ml, works out to sigma squared, multiplied by the trace of the inverse of XX transpose, exactly as shown in the lecture videos. Now, we want to make our estimator better. In other words, we want to reduce this mean squared error value. What options do we actually have? Sigma squared is the variance of the error, and that error is inherent to the experimental setup itself, whatever apparatus you are using to measure your variables, and so on. It isn't really something a data scientist can control directly. But the trace term, the trace of the inverse of XX transpose, is much more data dependent and deserves a bit more analysis. To lower our mean square error, we'd want to reduce this trace term specifically. How do we go about reducing it? Let's first look at the eigenvalues of XX transpose. Inside that trace term, if we call these eigenvalues lambda, then the trace of the inverse of XX transpose is simply the sum of the reciprocals of these lambda values. If we instead change this matrix from XX transpose to XX transpose plus lambda times the identity, we're effectively increasing every eigenvalue by that same lambda. We'll assume lambda is strictly positive. When we do that, we know that the reciprocal of a larger value is smaller, so the trace of this new modified matrix will be strictly lower than the trace of the original matrix. However, this changes the problem we're actually solving. Now, instead of solving using the inverse of XX transpose, multiplied by X transpose Y, we're solving using the inverse of XX transpose plus lambda, This extra term appears because the problem itself has shifted from what we originally set out to solve. We're now introducing a non-zero bias into our estimator, and that bias is exactly this extra term. It's non-zero precisely because we've deliberately modified the problem. Now, remember, we were originally chasing an estimator with lower mean squared error. So, let's see what difference this actually makes. If we compare the mean squared error for the original estimator, W hat ml, which had a zero bias, against this new ridge estimator, we get the following expression for their difference. In this expression, you'll notice the first two terms, one term, coming from the trace reduction, is strictly positive, since that's exactly the trace we deliberately reduced. Let's call this term A, and it's positive. The second term, the squared bias, is also strictly positive. So, we're looking at the difference between two positive quantities, meaning the overall result could, in principle, be either positive or negative. There's a genuine trade-off between these two effects. However, the existence theorem asserts that there exists some non-zero lambda for which this difference actually comes out positive. In other words, we can always find some lambda for which this new estimator achieves a lower mean squared error than our original W hat. That's one of the key reasons we're interested in this ridge solution. Given this formulation, we can now write down the ridge regression problem explicitly. The estimator we derived turns out to be exactly the solution to this optimization problem, which closely resembles the ordinary least squares optimization problem, but with this extra term added, lambda times the squared norm of W. This is our new regression objective, and conveniently, its closed-form solution corresponds exactly to that same formula, the inverse of XX transpose plus lambda, multiplied by X transpose Y. Another convenient property here, XX transpose is a scale version of your covariance matrix, and is therefore always positive semi-definite, since you can never observe negative variance. This means all of its eigenvalues are 0 or greater, though it's still possible for some eigenvalues to be exactly 0 if some of your variables happen to be correlated with each other. But if you instead consider XX transpose plus lambda times the identity, where lambda is strictly positive, every eigenvalue increases by exactly lambda. This means the smallest possible eigenvalue you could have is now lambda itself, which is strictly positive. So, this modified matrix, XX transpose plus lambda times the identity, is guaranteed to be positive definite, and therefore definitely invertible, compared to the ordinary least squares estimator, where we sometimes needed to rely on a pseudo-inverse to handle non-invertibility or singularity. Here we can guarantee, as a matter of fact, that the inverse always exists. That's another genuinely convenient property of the ridge estimator. Now let's compare how W hat, at varying values of lambda, compares to W hat ml. On the horizontal axis, we have the regularization strength, lambda, and each line in this plot corresponds to one particular weight. Since we have 50 features here, we get 50 separate lines. As you increase the regularization strength, you can see all these lines gradually decrease and converge toward 0. That's exactly what's happening as we increase regularization strength. We're pulling the entire weight vector, W, progressively closer to the origin, and that's exactly what's illustrated in this diagram. The next approach to regression is lasso regression. You'd be interested in lasso specifically when you want feature selection built directly into your modeling approach. How does that happen? Because we're using the L1 norm here, and the L1 norm's constraint region has these sharp points and edges, corresponding to certain feature weights being exactly 0. So, you're much more likely to converge on a solution with genuinely sparse weights, and that's exactly the scenario where you'd reach for lasso regression. Looking at the lasso solution, if we compare it against the standard W hat, we see that, past a certain point, there are drastic changes, where most weights abruptly drop to exactly zero. That's where sparsity kicks in. Interestingly, when one particular feature's weight drops to zero, you'll notice another feature's weight, for example, this grey line, actually jumps back up a bit, seemingly to compensate for the effect of the feature that just dropped out. So, in this context, lasso clearly gives us sparse solutions. We've now discussed how ridge regression and lasso regression can help us get a better approximation of our true underlying W. But how do we actually choose this hyperparameter, lambda? We know that the difference in mean squared error between our two estimators depends on lambda, but there's no closed-form way to directly compute the optimal lambda. We simply know that some good lambda exists. That's all we know. So, how do we actually find it? Secondly, remember, we don't actually have access to the true value of W in real practice. If we did, there'd be no problem to solve in the first place. So, how do we determine this hyperparameter without knowing the truth? There are a few strategies. The first is ordinary validation. We split our dataset into two parts, one set aside as a validation set, and the rest as a training set. We use the training set to learn our parameters, and then measure how well the resulting model performs on the validation set. We repeat this across all our candidate lambda values, and whichever lambda performs best on the validation set is chosen as our optimal lambda. The problem with this approach is that your validation set might not accurately represent the underlying problem. It could easily be biased, just by chance. To get a more principled way of choosing lambda, we instead repeat this process across multiple different splits, or folds, and that's where k-fold cross-validation comes in. In k-fold cross-validation, you partition your dataset into k separate parts. This k can be chosen based on your computational constraints, but, as an example, let's say we choose 5 folds. I'd split my dataset into 5 parts, and pick one of those parts to serve as my validation set, while taking the union of the remaining 4 parts as my training set. I'd train on that training set to get my estimator's parameters, then evaluate that estimator against the held-out validation set, repeating this process across all 5 possible choices of which fold to leave out gives me 5 separate error values, and I take the average of these as my overall error estimate for that particular lambda. Finally, out of all the candidate lambda values, I pick whichever one gives the lowest average mean squared error, and use that as my chosen optimal hyperparameter. When we actually do this, we find the optimal lambda changes. It was around 9 before, but we now get a somewhat different value. The final approach is leave one out cross-validation. We've already argued that k-fold cross-validation helps minimize bias coming from the validation set itself, but can we push this further? With k-fold, we split into, say, 5 parts. With leave one out, it's essentially the same idea, except now, instead of k-folds, you effectively have n folds, where n is the total number of samples in your dataset. So, essentially, what you're doing is leaving out just a single data point from your training set at a time, training on the remaining n-1 samples, and using that trained model to predict on the single point you left out. Everything else works the same way once you've made your prediction. You accumulate the resulting errors across every possible left-out point, take the average and use that average to rank and select the best candidate hyperparameter. Now, let's go through a couple of numerical examples for this week. The first question: the following weight vectors were learned from a 6-dimensional dataset using linear regression, ridge regression, and lasso regression. They're not necessarily corresponding in the order given, and we need to figure out which vector came from which method. First, notice that W1 has several exactly 0 entries, and only lasso produces genuinely sparse weight vectors, so W1 is most likely the lasso solution. Between the second and third vectors, recall that ridge regression essentially pulls the ordinary least squares estimate closer to the origin, so Comparing the two remaining vectors, whichever has the smaller overall norm corresponds to the ridge solution. And finally, since W2 is the one left over, that must be the ordinary least squares estimate. Now, let's go through a small example illustrating k-fold cross-validation. Suppose we have 450 training examples, and the reported error is calculated as the average across some number of iterations. Let's call it N1, where each iteration involves training a model on a subset of size N2 and evaluating its performance on a separate, disjoint subset of size N3. We need to figure out what N1, N2, and N3 actually are. We have 450 total samples. In threefold cross-validation, we'd split this dataset of 450 samples into 3 folds, each containing 150 samples. We fix one of these folds as our validation set, and take the union of the remaining 2 folds as our training set, train our model, and evaluate it, getting some error, call it E1. Then, we switch which fold serves as validation. Repeat the process and get a second error, E2. Then we repeat once more with the third fold as validation, giving us a third error, E3. So, we end up with a set of 3 separate error values, and the average of these 3 becomes the overall reported error for this particular choice of lambda. So, N1, the number of iterations, is 3. N2, the size of our training set in each iteration, is 300, and N3, the size of our held-out test set, is 150.
Welcome to Lecture 6 in Week 5 of Machine Learning Foundations. In this lecture, we'll move on to a topic that's a natural continuation of what we've learned so far, the singular value decomposition. We saw the spectral theorem in the previous lecture, which states that any real symmetric matrix is orthogonally diagonalizable. Here, we'll look at a more general class of matrices, ones that aren't necessarily square. They could be rectangular. We'll show that any rectangular matrix, with m rows and n columns, can be decomposed using 2 orthogonal matrices and a diagonal matrix. And this is what's called the ECD form, short for singular value decomposition. We'll show this decomposition holds for any rectangular matrix, and along the way, the proof will rely on the spectral theorem at some point. Before diving into singular value decomposition, let's do a quick recap of the spectral theorem, which was covered in a previous lecture, specifically for the real symmetric case. We've seen a more general version of this before, but let's recap it here. Suppose is an n by n real symmetric matrix. Then, the first claim is that all eigenvalues of a real, moreover, is orthogonally diagonalizable, meaning there exists an orthogonal matrix, let's call it Q, meaning Q transpose times Q equals the identity, such that it can be written as Q times a diagonal matrix times Q transpose. So you have this diagonal matrix sandwiched between Q and a collection of transpose eigenvectors, x1 transpose, x2 transpose, and so on, through xn transpose. Here, the diagonal entries are the eigenvalues of A, and these x sub i's are the corresponding eigenvectors of A. That's the spectral theorem. Just to reinforce this idea, let's work through a quick example, without going through every calculation in detail. Take a simple 2 by 2 matrix, with entries 1, -2, -2, -2. What are its eigenvalues? I'd recommend pausing the video here and working out this Q matrix and the eigenvalues yourself. The eigenvalues turn out to be -3 and 2, so λ1 equals -3, and λ2 equals 2. The corresponding eigenvectors are x1 equal to 1, 2, and x2 equal to -2, 1. Now, we normalize these 2 eigenvectors. There's no need for a full Gram-Schmidt process here. Just normalize each by dividing by its length. This gives us q1 equal to 1 over the square root of 5, and 2 over the square root of 5, and q2 equal to -2 over the square root of 5, and 1 over the square root of 5. Once you have these, you assemble the Q matrix using Q1 and Q2 as its columns. It's worth checking that Q transpose Q equals the identity. Whenever you're working through calculations like this, that's a good sanity check. Compute Q transpose Q and confirm it comes out to the identity matrix. If it doesn't, something has gone wrong somewhere, and you'd need to revisit your work. In this case, you can verify that it does check out. You can also verify that Q times the diagonal matrix of eigenvalues times Q transpose correctly reproduces the original matrix. Working through this product should confirm it does. So far, this has been a story for real symmetric matrices specifically. Now, let's move on to a more general decomposition. This spectral theorem, or eigen decomposition, is only guaranteed for real symmetric matrices. That's not to say other matrices can't sometimes satisfy something similar, but a real symmetric matrix is always guaranteed to have this kind of decomposition. The next topic we'll explore is singular value decomposition, which applies to any matrix at all, even rectangular ones. We'll focus on the real valued case here. Not every matrix can be diagonalized. We've already seen plenty of examples of that. However, any real m by n matrix, even a rectangular one, can be decomposed into what's called the SVD form. What does the SVD form actually look like? It can be written as A equals Q1 times sigma times Q2 transpose. Let's check the dimensions here. Q1 is an m by m matrix. Sigma is m by n, matching A's own dimensions, and Q2 is an n by n matrix. Additionally, both Q1 and Q2 are orthogonal matrices, meaning Q1 transpose times Q1 equals the identity, and similarly, Q2 transpose times Q2 equals the identity. Though these are different identity matrices, one is m by m, the other n by n. And finally, the matrix sigma has a particular form. It contains a diagonal block, D, with positive entries, sigma 1 through sigma r, where each sigma sub I is strictly greater than 0. Before going deeper into this decomposition, let's establish why it holds at all, why any real matrix can be broken down into a product of exactly these three matrices. Here's the proof. At some point, we'll need to invoke the spectral theorem. But first, notice that this decomposition is considerably more general than the one given by the spectral theorem, simply because we're not requiring symmetry here at all. It can be any matrix whatsoever, and moreover, we don't even require it to be square. Any m by n matrix works. Let's understand why this decomposition holds for any matrix, with a formal proof. Is m by n, so a transpose is n by n. What kind of matrix is a transpose A? Regardless of what it actually is, a transpose is always symmetric, and since A, by definition, has only real entries, computing a transpose still leaves you with real entries, never complex values. This fact means there exists a basis of orthonormal eigenvectors, let's call them x1 through xn, corresponding to the fact that a transpose can be diagonalized. This simply means we get enough eigenvectors, and since a transpose is on by n, we get independent eigenvectors, and we can also make them orthonormal. So, we have an orthonormal basis for n-dimensional space, corresponding to some set of eigenvalues. Now, let's start analyzing this further. We have a transpose A, the matrix we diagonalized, with x sub I as one of its eigenvectors. So, a transpose A multiplied by x sub I recurs lambda sub I times x sub I, for I running from 1 to n. Moreover, these x sub i's are orthonormal, meaning each has length 1, and the dot product of x sub I with x sub j is 0, for any I not equal to j. This confirms we genuinely have an orthonormal basis, each eigenvector has length 1, and they're mutually orthogonal. Continuing from here, if we take a transposer times x sub I and dot it with x sub I itself, we get lambda sub I times the dot product of x sub I with itself, which is just lambda sub I, since that dot product equals 1. But we can also compute this same dot product a different way. A transposer times x sub I dotted with x sub I equals the quantity a transposer x sub I transposed times x sub I, which is the same as x sub I transpose times a transpose A times x sub I, which is the same as, grouping differently, the quantity x sub I transposed times x sub I, and this, finally, is simply the squared length of the vector x sub I, a quantity that's always non-negative, purely by definition. So, combining these two calculations, called an equation 1 and equation 2, together they tell us that this dot product equals lambda sub I, and this same dot product is also non-negative, so lambda sub I must be non-negative. Now, recall that in the SVD, we end up with a diagonal matrix containing certain positive numbers, sigma sub I, some number, r, of them. Where do these actually come from? That's what we're building toward. So far, we have this let's order the eigenvalues of a transpose A, so that lambda 1 is the largest, then lambda 2, and so on, down through lambda r followed by lambda r plus 1, through lambda n. And here's what we find: to lambda 1 through lambda r are all strictly greater than 0, while all the remaining eigenvalues, from lambda r plus 1 onward, are exactly 0. Now, we can define our singular values. For each I from 1 to r, sigma sub I equals the square root of lambda sub I. So, we take the positive eigenvalues of a transpose A, there are r of them, take their square roots, and call those sigma sub I. There's a specific reason we take the square root here, because it's ultimately these values that go into our diagonal matrix. So we've now pinned down exactly what goes into the diagonal matrix, sigma. Now, let's figure out what goes into Q1 and Q2. Before that, we need a bit more analysis. Let y sub I equal 1 over sigma sub I times x sub I, for I from 1 to r. Let's understand the basics here. X sub I is an n-dimensional vector and is an m by n matrix, so y sub I lives in m-dimensional space. What's the length of y sub I? Since sigma sub I is positive, we can pull the 1 over sigma sub I factor outside, leaving us with the length of our x sub I, and that length turns out to equal the square root of lambda sub I, since sigma sub I is, by definition, exactly that square root. Dividing them out, this means every y sub I has length exactly 1. Why does the length of our x sub I equal the square root of lambda sub I? Well, from our earlier calculation, the squared length of x sub I equals lambda sub I. So, that's exactly y sub I's defining relationship. We can also show that, for I not equal to j, the dot product of y sub I and y sub j equals 1 over the product of sigma sub I and sigma sub j, times the dot product of x sub I and x sub j. This equals 1 over sigma sub I sigma sub j, times x sub I transpose, times a transpose A, times x sub j, but a transposer times x sub j, since x sub j is an eigenvector of a transpose A, equals lambda sub j times x sub j. So, this becomes 1 over sigma sub j, times x sub I transpose, times lambda sub j times x sub j, which simplifies to lambda sub j, divided by sigma sub j, times the dot product of x sub I and x sub j. But that dot product is exactly 0, since x1 through xn form an orthonormal basis and orthonormal vectors have 0 dot product with each other when their indices differ. So,
What we've shown is that the set y1 through yr forms a set of orthonormal vectors. This isn't necessarily a full basis, since these y's live in m-dimensional space, and r might be smaller than m. Since r is at most m, the set y1 through yr generally isn't a complete basis on its own. However, we can extend y1 through yr into a full orthonormal basis of m-dimensional space by adding in the remaining m minus r additional vectors needed. Let's denote this extended set, y1 through ym, as the orthonormal basis obtained by extending our original y1 through yr. Now we're ready to define q1. q1 is built from these vectors, y1 through ym, and for q2, we use the eigenvectors of a transpose A. So, all the pieces of our SVD are now defined. What remains is to verify that it actually equals q1 times sigma times q2 transpose. With this definition for q1 and q2, can we actually recover and sigma through this product? Let's check. Sigma should equal q1 transpose times A times q2. Working this out, a q1 transpose is just y1 transpose through ym transpose, stacked as rows, and a times q2 is just x1 through xn. If we can show that this product, q1 transpose a q2, has exactly the form we want, a set of diagonal entries, sigma 1 through sigma r, with zeros everywhere else, then we're done, and that's the last remaining piece of the proof. So, consider the ij entry of this product, q1 transpose a q2. That entry is simply y sub I, dotted with x sub j. There are two cases to consider here. First case, j is less than or equal to r. Recall, for indices up through r, y sub j has a specific form, y sub j equals 1 over sigma sub j times x sub j. So, in this case, y sub I, dotted with x sub j, and since x sub j equals sigma sub j times y sub j, this becomes sigma sub j times y sub I dotted with y sub j, which finally equals sigma sub j, if I equals j, and 0 otherwise, since the y's are orthonormal. Second case, j is greater than r. In this case, recall that a transpose x sub j equals lambda sub j times x sub j, but for all j greater than r, lambda sub j is exactly 0, by definition, since lambda r plus 1 through lambda n are all 0. This means x sub j itself must be 0, which means y sub I dotted with x sub j is also 0. So, putting both cases together, the resulting matrix, q1 transpose a q2, has entries sigma 1 through sigma r along its diagonal, and 0 everywhere else, exactly the r by r diagonal structure we were expecting for sigma. So, what we've shown is that q1 transpose a q2 equals sigma, which is equivalent to saying pre-multiplying by q1 and post-multiplying by q2 transpose, that q1 times sigma times q2 transpose equals A, and that's precisely the SVD of a. So, we've now shown that any m by r matrix can be decomposed into this particular form, a product of two orthogonal matrices sandwiching a diagonal matrix, where these two orthogonal matrices live in different spaces. One is m by m, the other m by n. We've also seen that q2, by construction, contains the eigenvectors of a transpose A. What does q1 contain? That's a question we'll answer next. Actually, just thinking about this decomposition a bit more, we can make an immediate remark about what goes into q1 and q2, purely from the structure of the decomposition itself, even without walking back through the full proof, since the equals q1, sigma, q2 transpose, consider a times a transpose. This works out to q1, sigma, sigma transpose, q1 transpose, which is exactly the eigendecomposition of a times a transpose. So, what goes into q1? The eigenvectors of a times a transpose, and a times a transpose, since it's a real matrix, is, importantly, also a real symmetric matrix, so we can apply the spectral theorem to diagonalize it, and sigma times sigma transpose will necessarily be a diagonal matrix that follows immediately. So sigma times sigma transpose is diagonal, and Q1 is made up of the eigenvectors of a times a transpose. Along similar lines, we can work out what a transpose corresponds to purely from the decomposition. This turns out to be Q2, sigma transpose sigma, Q2 transpose, which tells us that the eigenvectors of a transpose are going to Q2. Those are our closing remarks here. We'll work through an example next. As a summary of today's lecture, before we wrap up first, we worked through a simple example, computing the eigendecomposition of a real symmetric matrix, illustrating the spectral theorem in action. Then, we moved on to a very important topic, singular value decomposition, or SVD for short. We showed that any rectangular m by n matrix can be decomposed or written as a product of three matrices, two of them orthogonal, and a diagonal matrix in between, where these two orthogonal matrices have different dimensions, and the diagonal matrix itself is, naturally, also rectangular. What goes into the diagonal matrix are what's called the singular values, associated with the original m by n matrix. Importantly, singular value decomposition holds for any m by n matrix at all. We don't need to impose any additional structure, unlike the spectral theorem, which specifically required the matrix to be square, real, and symmetric. Here, no such structure is required at all. In the next lecture, we'll look at a simple example illustrating how to actually compute the SVD of a given rectangular matrix, and we'll work through that by example.
Welcome to the final lecture of this week. In this lecture, we won't introduce any new concepts. We'll simply work through singular value decomposition using a simple 2x2 example, but every concept we've learned so far will come into play. Specifically, we'll take a concrete matrix and write it out in SVD form. Since the example we're working with is a square matrix, the first thing to check is whether it's diagonalizable, and we do that by checking whether we can find enough linearly independent eigenvectors. Once we've settled that, we'll move on to writing it in a CD form, working through the computation in full detail. So, let's work through an example to understand SVD. Even though it's just a small 2x2 matrix, the concepts and procedure for deriving the SVD of any given matrix should become clear from this example. Let's take a particular matrix, A. The first thing to notice is that it isn't symmetric, so we can't directly apply the spectral theorem to claim it's diagonalizable. Our task, though, is to find the SVD of a. Now, for matrices that happen to be diagonalizable, the SVD ends up matching exactly what the spectral theorem would give us, so in that case, we wouldn't need to work quite as hard. So, the first thing to check is whether this particular matrix is diagonalizable. Let's check. It turns out the answer is no. The eigenvalue here is simply the square root of 2, and it's repeated. But that alone isn't enough to conclude the matrix isn't diagonalizable. If we can find two linearly independent eigenvectors, we could still diagonalize any 2x2 matrix, even with a repeated eigenvalue. So, let's check what a minus the square root of 2 times the identity looks like. This is a minus lambda times the identity, and it works out to a matrix with entries 0, 1, 0, 0. From this, we find that the vector 1, 0 is an eigenvector, but we can't find another linearly independent eigenvector alongside it. There simply aren't any more linearly independent eigenvectors ever available, so it's clear this matrix cannot be diagonalized. So, the reasonable next step is to instead compute its SVD. Let's find the SVD of this matrix, whose entries are the square root of 2, 1, 0, and the square root of 2. Here's the overall procedure. Find the eigenvalues and eigenvectors of a transpose A, using these eigenvectors to build an orthonormal basis.
In this case, that basis lives in two-dimensional space. After that, use the defining relationship from the proof, sigma 1 times y1 equals x1, and sigma 2 times y2 equals x2, where x1 and x2 come from the basis found in step 1. Use this relationship to solve for y1 and y2. Finally, assemble q1 from y1 and y2, q2 from x1 and x2, and sigma is the diagonal matrix with entries the square root of lambda 1 and the square root of lambda 2, where lambda 1 and lambda 2 are the eigenvalues of a transpose A. So, that's the overall procedure. Let's work through it fully for our matrix. Step 1, we compute a transpose A, which comes out to a matrix with entries 2, the square root of 2, the square root of 2 and 3. This is, of course, a real symmetric matrix as expected. You can work out its eigenvalues yourself fairly easily. They come out to lambda 1 equals 4 and lambda 2 equals 1. So, the singular values are sigma 1, the square root of lambda 1, which is 2, and sigma 2, the square root of lambda 2, which is 1. So we're already set to start assembling our diagonal matrix, sigma. The next step is finding the eigenvectors of a transpose A. Since the eigenvalues are 4 and 1, let's start with a transpose minus 4 times the identity, which comes out to a matrix with entries negative 2, the square root of 2, the square root of 2, and negative 1. And a transpose minus the identity comes out to entries 1, the square root of 2, the square root of 2, and 2. Now, simply by inspection, an eigenvector for lambda 1 equals 4 is the vector with components 1 and the square root of 2, and an eigenvector for lambda 2 equals 1 is the vector with components the square root of 2 and negative 1. Now, we need to normalize these eigenvectors. Doing so, we get two vectors. Let's call them x1 and x2. Dividing by its length, x1 becomes 1 over the square root of 3 times the vector 1 and the square root of 2, and x2 becomes 1 over the square root of 3 times the vector, the square root of 2, and negative 1. Given x1 and x2, what are we ready to define? Going back to our earlier procedure, we can now define q2. q2 is simply formed from x1 and x2, so, with that common factor of 1 over the square root of 3, q2 is now fully defined. Moving to step 2, we use the relationship sigma 1 times y1 equals x1 and sigma 2 times y2 equals x2 to solve for y1 and y2. Since we already know what x1 and sigma 1, working this out, y1 comes out to 1 over the square root of 3 times the vector 1, 2. Now we're ready to define q1 using y1 and y2. By definition, if you check back through the proof, since sigma 1 times y1 equals x1, by construction, y1 and y2 will automatically be unit length and orthogonal to each other. The last thing to verify is step 3. We've now obtained q2 from x1 and x2, q1 from y1 and y2, and sigma, the diagonal matrix with entries 2, 0, 0, 1. As homework, I'd encourage you to verify that q1 times sigma times q2 transpose actually reproduces our original matrix A. Work through that computation yourself to check it holds. Just a very short summary before wrapping up in this lecture. We simply applied the concepts we learned in the previous lecture, decomposing a given matrix into SVD form, and we did this in the context of a simple 2x2 matrix. At the outset, we also had to run a sanity check if a matrix happened to be diagonalizable. Its eigen decomposition is already its SVD form. However, the particular example we worked through in this lecture was not diagonalizable, which we verified directly, and so we instead constructed its SVD by computing the appropriate singular vectors, along with the left and right eigenvectors of the relevant matrices. Once we did that, we were able to express our original matrix in SVD form, as a product of an orthogonal matrix, a diagonal matrix, and another orthogonal matrix, and the entries that make up these orthogonal matrices have a clear, logical interpretation. They are the eigenvectors of either a transpose A or a times a transpose, depending on whether they sit on the left or the right of the diagonal matrix in the decomposition.